The objective of the experiment is to determine the line charge on two charged pieces of tape and calculate the electric and gravitational forces on the top tape. This is accomplished by experimentally determining the charge of the pieces of tape in a point charge model and then comparing that experimentally calculated value to a computational line charge model. The magnitude of the charge was experimentally determined by levitating two tapes over one another by balancing the gravitational force and electrical force of the tapes. The distance at which the tapes levitate is noted and used for subsequent calculations. The point charge model was used for all experimental calculations. A more accurate calculation of the overall charge of the tape and subsequent forces being experienced by the tape is computationally derived using the line charge model as opposed to the point charge model. Fundamental physics principles included the like charges repel and opposite charges attract, the equation of force equals mass times acceleration, and the equations for calculating the electric field and the force caused by the electric field are all shown here on the slide. All these principles and equations help us to determine the magnitude of the electric field by algebraically and experimentally balancing the net gravitational force and net electrical forces of two pieces of tape. This subsequent slide, which includes my code and model, will outline the algebra of how line charge method was implemented. The code for glow strip model, along with the algebra, is given on the left-hand side, while the model and some conclusion questions are answered in the window on the right-hand side. Each line of spheres represents a piece of tape modeled as a line charge. It's important to note that each piece of tape has the same charge. The green arrows are the net force experienced by the line charge as a result of the product of the net electrical field and their respective charge. The gravitational and electric forces of the line charge model are equal and opposite with a magnitude of 2.1582 e to the negative 3 coulombs. This is why the top piece of the tape levitates, because the net electrical force experienced by the line charge pushing it up is equal and opposite to the net gravitational force pulling it down experienced by the top line charge. Through using the point charge and line charge model, correct equations and performing simple algebra, it was concluded that the charge of the tape was larger by 22.88% in the line charge model when compared to the point charge model. Some additional questions. The length of my tape was 0.16 meters in length. The mass was 0.00022 kilograms. They levitated when they were 0.045 meters apart. The magnitude of the gravitational force was experimentally calculated to be 2.1582 e to the negative 3 newtons. The electrical force was experimentally calculated to be 2.158 e to negative 3 newtons. The magnitude of the charge of the tape was calculated computationally to be 2.70789 e to the negative 8 coulombs. The charge is evenly distributed along the length of the tape is the assumption that we made. And number 8, experimentally it was determined that when implementing the point charge model, the calculated charge of the tape is determined to be 2.20362 e to the negative 8 coulombs. When I used the line charge model, I computationally arrived at a charge value of 2.70789 e to the negative 8 coulombs. The difference in experimental and computational charge is 22.88%, with the computational charge being larger. The electric and gravitational forces of the line charge model are equal and opposite with a magnitude of 2.1582 e to the negative 3 coulombs. These estimates differ because for the computational charge calculation, it was assumed that the charge was evenly distributed along the entire length of the tape, not just a single point like in the point charge model.